All right, welcome back. Today, we're going to decode the secret language of energy. You know, the energy that's literally all around us. We're going to figure out how chemists write down the, energy price tag for every single chemical reaction. We're talking everything from rocket fuel to the sugar that's powering your body right now. So let's just dive right in.
So it really all boils down to a super simple question. Why does a campfire feel so warm, but an instant ice pack feels, well, instantly cold? I mean, you felt this, right? That amazing radiating warmth from a fire, and then that biting cold from an ice pack. They feel like total opposites. And guess what? Chemically speaking, they are. And today, we're going to find out exactly why, using the language of thermochemistry.
Yeah, so on one side, you've got reactions that just give off heat, like a campfire, right? They're releasing all this energy out into the world. But then on the other side, you've got reactions that actually pull heat in from their surroundings, which is why things feel cold. And the coolest part is, chemistry has this incredibly precise way to describe and measure the energy involved in both of these things.
And that brings us to the main tool we're going to use today, the thermochemical equation. Now, I want you to think of this like a recipe. You know how a normal chemical equation tells you the ingredients, what you start with and what you end up with? Well, a thermochemical equation does that, plus it tells you exactly how much energy gets cooked up or used up in the whole process. It's the full story.
So what is this thing exactly? Well, it's basically the complete picture of a reaction. It's a balanced chemical equation, sure, but it doesn't just stop there with the chemicals. It also tells you the physical state of everything involved, like is it a solid, a liquid, or a gas? And this is the most important part. It includes the energy change. We call that enthalpy, or you'll see it as delta H.
Okay, so let's break down those three key parts of the recipe. First, you've got your standard balanced equation. No surprises there. Second, you'll see these little letters in parentheses, S for solid, L for liquid, and G for gas. And trust me, these are super important because changing the state of something actually costs energy. And then third, the absolute star of the show, delta H, the change in enthalpy. This is our magic energy number.
All right, check this out. This is our master example for today, burning sugar, or glucose. So we've got solid glucose reacting with oxygen gas, and it produces carbon dioxide gas and liquid water. But now look at that last line. See it? Delta H equals negative 2,808 kilojoules. That negative sign, that's the secret code. It tells us that for every single mole of sugar we burn, a whopping 2,808 kilojoules of energy are released, pushed out into the world.
Now, a quick side note, but it's important. To make sure all scientists are comparing, apples to apples, these energy values are usually measured under what we call standard conditions. That's just 1 atmosphere of pressure and a pretty comfortable 25 degrees Celsius. It just creates a level playing field, so the energy value for a reaction in a lab in one country is totally comparable to another one halfway across the world.
Okay, so let's get back to our campfire and that instant ice pack. These two things perfectly represent the two fundamental flavors of energy change in chemistry. You've got reactions that release heat, and you've got reactions that absorb it.
So, here's the deal, and if you remember one thing, make it this. It's all about the sign of delta H. For an exothermic reaction, like our campfire, energy is basically a product. It's released, it feels warm, and that delta H is negative. Now for an endothermic reaction, like the cold pack, energy is a reactant. It's absorbed, it feels cold, and the delta H is positive. So just think, negative means heat exits, positive means it's pulled in. Simple as that.
And you know what's cool? This isn't just for big, dramatic chemical reactions like explosions or fires. Even something as simple and everyday as water changing its state, going from solid ice to liquid water to gas, that's a thermochemical process, and it has its own energy price tag.
Let's start with melting. The amount of heat you need to melt 1 mole of a solid is called the molar enthalpy of fusion. So for water, it takes 6.01 kilojoules of energy to melt 1 mole of ice. And notice that delta H is positive. Why? Because the ice has to absorb that heat from whatever's around it to melt. It's an endothermic process.
Okay, so what about boiling? Well, that's called the molar enthalpy of vaporization. And get this is where you really see the energy costs. It takes over 40 kilojoules of energy to turn 1 mole of liquid water into steam. That is almost 7 times more energy than it takes just to melt the ice. And why is that? Well, to make steam, you have to completely break all those little bonds that are holding the water molecules together as a liquid. That takes a ton of energy.
This table just sums it all up perfectly. Check it out.
Melting and vaporization, they both absorb heat, so they've got a positive delta H. Now the reverse processes, freezing and condensation, they do the exact opposite. They release the very same amount of energy, which means they have a negative delta H. It's this beautiful fundamental symmetry you see all over in nature.
Okay, so why does any of this matter? Who cares about these equations? Well, because they aren't just some abstract thing for a chemistry lab. They actually describe the fundamental processes that power our entire world, from what's happening inside your body right now to the rockets that are taking us to the stars. Let's connect this to the real world.
Okay, let's put this into practice. Let's do a real calculation. Using that glucose equation we looked at earlier, can we figure out exactly how much heat is released when we burn 54 grams of it? That's only about 3 tablespoons of sugar. What do you think?
You bet we can, and it's a really simple two-step process. First, we just convert the grams of sugar into moles. We use its molar mass for that. That gives us 0.3 moles. Easy enough? Second, we take that number of moles and we multiply it by the energy value from our thermochemical equation, which, if you remember, was negative 2808 kilojoules per mole.
And boom, there's our answer, negative 842.4 kilojoules. That negative sign confirms that energy is being released. And listen, that is a serious amount of power from just a few spoonfuls of sugar. We're talking enough energy to take over 2 liters of water from room temperature and bring it all the way to a boil.
But here's the most amazing part. That exact same reaction, it's happening inside your cells right this second. The process of cellular respiration is basically just the slow, controlled combustion of glucose. Your body is harvesting that exact same 288 kilojoules of energy per mole to power every single thought, every movement, every heartbeat. You are literally a walking, talking thermochemical reaction. And if you zoom out to a larger scale, this kind of combustion powers our entire civilization. The energy that's released from burning gasoline in our cars or natural gas to heat our homes, it's all described by these same thermochemical equations. Understanding the enthalpy is what tells us how efficient these different fuels are.
And if you want the ultimate example of just raw power, look no further than space exploration. That massive, explosive combustion of hydrogen and oxygen in a rocket engine, it releases such an incredible amount of energy that it's enough to overcome Earth's gravity and literally push a shuttle into orbit. I mean, that is thermochemistry on a truly epic scale.
But it's not always about explosions and raw power. It can also be incredibly clever and subtle. Get this, some farmers will actually spray their crops with water right before a predicted frost. Why on earth would they do that? Because as that water freezes on the plants, it goes through an exothermic phase change. It releases a tiny amount of heat, but it's just enough to keep the plant's tissues from freezing solid and getting destroyed. How clever is that?
So, what are the big takeaways here? What should you remember from all this? First, think of thermochemical equations as energy recipes. They tell the whole story. Second, that sign on the delta H is your guide. Negative means heat is released, exothermic. Positive means heat is absorbed, endothermic. And finally, these really simple rules explain this huge range of things, from melting ice in your drink to powering rockets to the stars.
So the next time you feel that warmth coming off a fire or the chill from an ice cube melting in your drink, I want you to remember what you're really experiencing. You're feeling the universe literally balance its energy books. And now you know how to read the receipt. Thanks for tuning in.